everyone. Here is a video for our week 5, and this is on one sample hypothesis tests. Like before, this is not intended to get you through everything in the entire week. It's to give you a start and to give you a big idea of what's happening in this topic. Okay, I'm happy to make another video if you have questions on other things or want to expand on this, or we can just talk about it in class as well. But this should give you a good start as to what's happening. So here is an example. Okay, if you look at IQ tests, there are called standardized tests, and they're normed so that the mean IQ for normal people is 100, and the standard deviation is 15. That's just how they're made. They're designed to be that way. But we have some data. Here is the source of that data, but I happen to have it in a spreadsheet over here of children who live near a smelting plant. All right. And when you look at their IQ, let me pull that up again because I already have it here. I'm going to get rid of all this. When you look at their IQs, the mean IQ for these children is 90.818, and this is the standard deviation for those children in the sample. And the N, let me use count and count all of these. The N is 121, so there are 121 children that they used in this study. So this looks like a low IQ, and we think it's probably due to the lead, but we don't know if it's really low or if it's just due to the fact that the sample that we had. It could be that we just happened to pick children in our sample that had lower IQs. Even though it was a random sample, it's possible that that could happen. So we don't know how to tell. That's what a hypothesis test is intended to do, is to tell us if this is significantly high or significantly low from what is claimed or what is known to be true in general. That's the idea of a hypothesis test. So let's look at our next slide. Hypothesis test, also called a significance test. Like I just said, it's a procedure that's developed to test the truth of a claim. Okay, it's used in more situations than what we have now. We'll be doing hypothesis tests for the rest of the semester. What we're doing this week is one certain type of hypothesis test. And the type we're going to do this week will be comparing a single sample, so we're doing one sample hypothesis test, to either a known population or a claim about a known population. That's the idea. Let's go through kind of the process. It's going to seem very long and complicated, but hopefully by the end of the class, it's going to feel like a piece of cake because we're going to do it over and over and over and over and over. But the idea is, you start with two competing hypotheses. One is called the null hypothesis, the other one is called the alternative hypothesis, and they contradict each other, so they both can't be true. Only one of them can be true. Then you try to come up with evidence to see if you should believe the alternative hypothesis and reject the null hypothesis, or if you don't have enough evidence to reject the null hypothesis and you have to stick with it. In a way, it's almost like our court system. People are innocent until proven guilty. Okay, they go to trial. People bring evidence. If there is enough evidence, then you revert from saying, yes, we think this person is innocent, to saying, yes, there's evidence that this person is guilty. The same thing here. We start off assuming that nothing is amiss, that everything is always like the claim, everything matches the population, whatever it is. We look for evidence to see if we can disprove that. Okay, although we never can completely disprove it, we'll talk about that at the very end of this. So that's the idea. We've got two competing hypotheses. We try to get evidence to try to reject one of them and see what's going on. Okay. Now, our null hypothesis always has an equal sign in it. For means, we're going to say that the mean of our sample equals the mean of the population. Okay? For proportions, we're going to say that the proportion of our sample equals the proportion of our population. The alternative hypothesis is going to say, no, that's not true. And it can have one of three forms. It can either say less than, that the sample mean is less than the population mean, or that our mean is larger than the population mean, or that it's not equal. This is called a two-tailed test. These two are called one-tailed tests, and you'll see why they're called that in a minute because we'll have a picture. And the one with the less than or equal, since it's pointing to the left, that's called a left-tailed test. The other one's called a right-tailed test. And the picture will show you what we mean by that in a little bit. So we come up with our hypotheses. The next thing we do is we determine a significance level. Just like confidence. Remember last week I talked about how we get to decide how confident we want to be. So we also get to determine our alpha. The alpha is the maximum probability we can risk being wrong. Okay, that's the maximum that we decide we're willing to take if we make a mistake. And we decided, of course in the homework they'll tell you what the alpha is, but in practice you get to decide. Okay. And then we determine what distribution we're going to use. So we're kind of setting the stage for the trial. Okay, we come up with our claims, okay, guilty or innocent. We decide how certain we want to be. We figure out what distribution to use. These are like coming up with the motions before the trial, things like that. So if, just like last week, if we're working with proportions, we're going to use a Z. And in the template, we're going to use the proportion template. For means, it depends on whether we know the sigma or not. If sigma is known, we're going to use the Z, the one sample Z template. If sigma is unknown, we're going to use the t-test template. Okay, or we can do these by hand. Alex also steps you through doing it by hand, and I'll do this both ways so that we can compare. All right, so let's go to the next slide and continue on with our process. After we do that, we gather all our evidence. Okay, we get a critical value, and I'll show you how to calculate that in a little bit. That's something that is determined by alpha. So the critical value says if you're on one side of the critical value, you're going to reject the null hypothesis. On the other side, you're going to say we're not going to reject the null hypothesis. It's like the dividing line between saying innocent or guilty. We're going to get a test statistic. That comes from our sample. And that's just the normal values that we get for Z or T, however we've calculated those before. All right. And then we get what's called a p-value. And that's determined by our test statistic. The p-value is important. We'll talk about that in more detail at the end when we talk about errors, our p-value. Then we're going to draw a picture, which I will do for you several times. And then we're going to compare our sample to a population to draw a conclusion. And we're going to have two methods to do this. One is called the critical value method. The other one is called the p-value method. And I've got that on another slide before. Both methods will give you the same result. It doesn't matter which one you use. Okay, although sometimes the homework will tell you to use one, sometimes it will tell you use the other. But in practice, if you use the critical value method or the p-value method, you will get the same final result about whether it's innocent or guilty. And then we state our conclusion in everyday language, and we have two choices. We either reject the null hypothesis or we fail. Let me fix that. We fail to reject the null hypothesis. Those are our two final conclusions. Okay? So let's come back and look at our example. For normal children, the mean is 100, the standard deviation is 15. For our sample data, our X-bar for our sample was 90.818, and our standard deviation was 14.4265, although I don't think we're going to need that. Let me move that down there. Okay, so that we've got it all together. So there's our data. Now, our hypotheses. The null hypothesis always has an equal in it. We're looking at means, so my null hypothesis is going to be means, and we're going to say the mean is equal to 100, not our sample from our population. Okay. Our alternative hypothesis will also have a mu and a 100 in it, and we have to decide whether we're going to use a greater than, a less than, or a not equal to. If there is some outside reason that you should use a greater than or a less than, that's when you use a greater than or a less than. Otherwise, use a not equal. In this case, we're talking about children who've been exposed to lead. So I think that we have enough of a case here to use a less than. Okay, so we're going to say that the mean is less than 100 for our hypothesis. We're going to set an alpha. I'm going to set an alpha of 1%, 0.01. Okay, so that's what we've got so far. And we're going to determine a distribution. Let's see, we're working with means. And since we're working with means, I need to see if I know the sigma or not, and I do. Sigma is known. That tells me that I'm going to use the Z distribution right there. So I've got a picture right here. Okay. So I'm going to do this with the template first, and then I'm going to do it with the by hand with Alex so that we can compare these two methods. Okay. We know we're using Z, so I'm going to use the Z template. That's the T template. Here's my Z test template right here. And remember last week we looked at the confidence intervals. This week, because we're doing hypothesis tests, we're not going to use that box. We're going to use the box that says hypothesis test. Now, if you look at the copy that I sent you, you're going to see that there are some extra things in here that aren't in it. I'm going to post this. I've just added some new commands in here to give you more information. Okay, so I'm going to post this for you this week. So let's take a look and see what it wants. It wants the sample mean. Okay, our sample mean was 90.81818. It wants our hypothesized value. So I look at the hypothesis, and the hypothesis says 100. It wants the sample size, which I remember was 121. And it wants the standard deviation. Now I have two standard deviations here. I've got the population standard deviation, and I've got the sample standard deviation. You can always calculate the standard deviation for the sample no matter what. That's not what we need here. We need the sigma. When you're working with the Z test, you're going to use the sigma. Just like last week in our DQ, we used the 2, not the whatever standard deviation you got for your sample. Our significance level, we decided we were going to have it be 1%. So I'm going to enter in 0.01. And it's going to give me a lot of values. So let's look at these values and see what they're telling us. I'm going to try and move this over here out of the way, and we're going to draw a picture. Let's see if I can do this. Okay, our hypothesized value was 100. That goes right in the middle here, and that corresponds to a Z value of 0. Okay. Our Z statistic was negative 6.7. We're going to look at that later. Let's put our critical value and our alpha in. We decided we're doing a left tail. In fact, let me just copy this so I don't have to go back and forth here. kind of fits in the middle like this, and I'll make it a little smaller, I hope. There, it'll fit just right. Okay. Okay, our alpha was 1%, and our critical value goes with the alpha, and we're doing a left tail. So I don't need the right, and I don't need the 2. I don't need the right, I don't need the 2, I don't need the 2, I don't need the right, and I don't need the right. We're doing a left tail because that points to the left. So my critical value is a negative 0.2326. This is my critical value. That's the dividing line between rejecting and not rejecting. Okay, that comes from alpha. This area here, that area is alpha. That area, okay? And the dividing line between our alpha and our non-alpha is the critical value, the negative 2.326. Now our p-value, it says 0. Okay, it goes with our z statistic. Our z statistic is negative 6.733. So if I continue this scale out, this thing really goes on forever in both directions. Maybe use another color here. Negative 6.733. That's the z value for our data. If I converted my data to a z, that's what I would get. So that comes from our data. Here's what the p-value is. It's this little area out here. And that's so small it doesn't even show up. It's so tiny. Let's come back to the spreadsheet for a minute. If I change this to standard deviation, or not standard deviation, to scientific notation, oh my gosh, yeah, it's so small that we can't even see it. It's 6.73. Oh, that's my, let's turn that to scientific notation. That's 8.29 times 10 to the negative 12th. That's how small it is. That's tiny. Okay, that's the area to the left of our test statistic. That's the probability that under these conditions, with a mean of 100 and a standard deviation of 15, this is the probability that we would get a sample of 90.8 or less. It's possible that that could happen, but it's a very small probability. So that's what this is saying. Okay, we claim that the mean is 100 and the standard deviation is 15. If that claim is true, then our results have a probability of happening so small that we just can't believe it really could happen. That's what this is saying. So therefore, we're going to say this is just too rare for us to believe that we could have actually had it happen. We're going to say that this is probably different than the 100. Okay. I can also do this in ALEKS using what we've got. So I'm going to run through that as well with the ALEKS commands. Yes, ALEKS is still open. Make that a little smaller because I need the ALEKS calculator. That's all I'm doing here is just getting the calculator. Okay, so our mean is 100, our population standard deviation is 15, our X is 90.818. Okay, our critical value comes from our alpha. Let me put my alpha in here. Okay, so in this case, I'm not going to draw these in. I'm just going to put my critical value, and this area here is my alpha, and it's 1%. So I'm going to find the critical value first. That means I need to find the z-value that separates the bottom 1% from the top 95%. So because I want a z-value, I'm going to come to this command, and I'm separating the bottom 1% from the top 99%, so I'm entering my 99, and the z-value is negative 2.326. That's my critical value. So that's how I'm going to find that. Okay. The next thing I'm going to do is get my test statistic. I'm going to use the z-value for that, so I'm going to take my x value minus my mean over my standard deviation, and because we have samples we're looking at means, I'm going to divide that by the square root of n. It's the standard. All right, so that I just do with a regular calculator. I'm going to do it in Excel so that you can see how you could do this quickly in Excel. And I'm not going to try to put the whole formula in all at once. I'm going to do the numerator, and I'm going to do the denominator, and then I'm going to get my test stat. So the numerator is x minus mu. So there's my x. My mu I know is 100. So my sample mean minus my population mean. My standard deviation is sigma, which was 15. Remember, we're not going to use the sample, we're going to use population, divided by the square root of 121 was my n. And to get my test statistic, it's the numerator divided by the denominator. There's my test statistic, negative 6.7333. So out here somewhere, that's my test statistic. And my p-value now is this little area right here. So it's going to be the area that's to the left of negative 6.7333. Because it's an area, I'm going to use the probability. Let's pull up our little Alex calculator again. I want the probability that z is less than negative 6.7333, and that's 8.3 times 10 to the minus 12. See that minus 12 up there? 8.3 times 10 to the minus 12. So that's very small. Our actual data is so far away from the mean. The mean is 0, which corresponds to our 100 when we convert to z-values. Okay, our actual sample is so far away from the mean, it's farther away than the critical value. That critical value is the dividing line. So we're going to say, yes, this is significantly low. It's very low. Okay, so here's our conclusion. If the critical value is between the mean and the test statistic, if the test statistic is outside in the tails, we're going to say we reject the null hypothesis. If it's not between those, then we're going to say we fail to reject the null hypothesis. That's how we do it with the critical value method. With the p-value method, we look at these areas. If this purple area is smaller than the pink area, then we reject the null hypothesis. And you can see, yeah, definitely it is. Okay, so if the p is less than our alpha, we reject the null. So here we know that 8.29 times 10 to the negative 12 is less than 0.01, which is our alpha, and that's our p. So we're going to reject. we're going to say we have evidence to reject the hypothesis that the mean is 100. We have evidence to conclude that the children who've been exposed to this lead have a lower IQ than the population. Next slide. Let me get this going. Okay, here's a quick summary. I've got a little bit more to talk about errors in here as well. Okay, if you're working with means and sigma is known, you use Z. If you're working with means and sigma is unknown, you use T. If you're working with proportions, you use Z. If you're working with variances, you're going to use chi-squared, and I'm not going to talk about that in this lecture, but we can do a little bit if you want later on. Your critical value depends on alpha. It's your dividing line between reject and don't reject. Your test statistic depends on your sample. Your p-value depends on your test statistic. You reject the null when either the test statistic is outside of the critical value in the tails, or if the p-value is less than alpha. You fail to reject the null if the test value is inside, or if the p-value is greater than alpha. So there's kind of a quick summary of how this works. All right, got a little bit more to talk about. This is not foolproof. This is all based on probabilities. That p-value is the probability that even though you followed this process correctly, that your sample really does have a problem with it. Okay, so there are two types of errors that come into play. One of them is called a type 1 error, and I think of that as a false positive. If you go have a medical test for a disease and they come back and they go, yes, you do have diabetes, that's a positive result. Okay, the test said, yes, you have positive result, that you're not like normal, something else is going on, you're special. Okay, so the probability of a false positive is a type 1 error. That's when you reject the null hypothesis, but the null hypothesis is actually true. The p-value is the probability of a type 1 error. DQ1 right there, p-value. Okay. There's another type of error called a type 2 error. Even though you've done all these steps correctly, it could be that the sample just wasn't a representative enough sample. A type 2 error is the probability of a false negative. That's the probability that you fail to reject the null hypothesis, but the null hypothesis is actually true. Now, these are little tongue twisters. Okay, you've got a few homeworks that talk about type 1 and type 2 errors. You may have to write out steps a little bit at a time. You might have to say type 1, fail to reject null, and then you have to write mu equals 100 to keep that track in your head, but null is true. Okay, so probability of saying mu is less than 100 because that was our alternative, but actually mu is equal to 100. You may have to write out some steps like that just to keep everything straight when you answer those questions, because they can be a little twisty and tricky. Okay, just wanted to let you know that. Okay, now, if you have a right tail test, the picture is pretty much the same, except your critical value is going to be here, your mean is going to be here, your alpha is going to be on the right. Okay, and then your test statistic is either going to be out in here or out there, either one, but again, the p-value is whatever area to the right of your test statistic. So it's the same idea, it's just that you're on the other side of the table. For a two-tail test, things are a little bit different. Your mean is still in the middle, but what's different is that you have two tails, and each of these tails add up to alpha. So this is half of alpha here, and this is half of alpha here. Okay, so if you're doing a 10%, if alpha equals 10%, then this would be 5% here, and this would be 5% here. And then when you find your test statistic, I'm going to put it in the tail. If your test statistic is right here, half of your p-value would be here, and half of your p-value would be there. For a two-tailed test, you have two critical values, one up here and one here. They're opposites of each other. So when you get one of them, say one of them is 1.963, the other one would be negative 1.963. So in ALEKS, when they ask you for a two-tail for critical values, be sure to give both. It'll tell you that you're wrong unless you give both of them there. If you want to see a two-tailed test, let's talk about it in class. Again, I haven't talked about variances. I don't want to make this video too long. So if you want to talk about variances, let's talk about those in class as well. I hope this gives you a good start. Thank you all very much for watching this video, and I hope it helps, and I'll see you in class. Bye-bye.